Okay, so welcome to this video session. So today we're going to discuss the solutions on your previous quiz, particularly on the problem solving. So number one, we can see here the details of the truss and cord, wherein the value of P is set to be 30 kilonewton and it is inclined at 15 degrees with the horizontal. So given the width of the bottom cord member, that is equivalent to 200 millimeter, we can see it here. We're gonna determine the value of y and the value of x on the condition that the allowable bearing stress is 5 megapascal and the allowable shearing stress is 65 megapascal. So this is actually a notch, okay? So between this inclined member here and the bottom cord, we have a notch. So a notch is a technique in the carpentry wherein there will be an interlock between these two members. And eventually, because of that setup, and this is inclined at a certain angle, there will be a transfer of component of this inclined member to this bottom cord, and that will cause this cord to be stressed in terms of bearing and shearing stress. So first, if I'm going to have my projection of the load here, say this is the load that is inclined. So the effect is there will be a horizontal force and a vertical force that will be developed out of this P. So let us place here the value. Say we have here 30 kilonewton. Okay, so this is inclined at 15 degrees with respect to the horizontal. So this horizontal component has actually two effects on the notch here. So number one effect is that this particular section, say I'm gonna shade this one, will be in a direct contact to that of the diagonal member. If that is the case, we have here a type of stress, and that stress is actually a contact. When we say contact, we have a bearing stress. So we're going to apply the bearing stress formula to come up with the value of y. Okay, so the y dimension. Say actually this is y. Okay, and of course the width is 200. So that is the one of the effect of this horizontal component of 30. And another one, this will tend to tear this horizontally also. Okay, so if your horizontal is applied, or the horizontal component of 30 will have a cutting effect on this particular section. So as we can see here, from this one, this is already cut because of the shear resistance against the direction of your force. So this is the shear force. Okay, and by summation forces horizontal, this is the horizontal component of P. Say this is P horizontal. So this is P horizontal. So regarding with the vertical component, we are not concerned with the vertical because the effect of the vertical will be tearing this particular section at this, but we are not concerned with this dimension. So we will just focus ourselves to the horizontal P here. So we're going to get the value. So of course, horizontal component is adjacent to your reference angle. So we're gonna use function of cosine since we have an adjacent location of this force to the reference angle. So therefore, PH is equal to 28.98 kilonewton. Okay, so now that we have obtained that value, we can now apply the bearing stress formula. Say for bearing, we have sigma is equal to P all over A. So the bearing force is substituted as well as the area of the bearing area. So the allowable for bearing you can see here is 5 megapascals, and simply we determine PB, and that bearing force is actually the horizontal component also. So we have here 28.98. Of course, this should be multiplied by 1000 to make it in newtons. Okay, and then for the bearing area is the shaded portion you can see here in the figure. That is 200 by y. So therefore, by cross multiplication, y can now be derived to be equal to 28.98 millimeters. Okay, so next, considering the shearing, say for shearing, we'll just use the shearing stress formula. Tau is equal to V all over A. Okay, so the allowable shearing stress here is 65. This is equal to the same force, that is 28.98 times 10 cube. Okay, so for the shearing area, you can see here the shearing area. Say that this is the area is being cut. So in the problem, this is X. Okay, and the width is given to be equal to 200 millimeter. Okay, you can see it here. So just write it in here, 200 by X. So by cross multiplication, X will now be equal to 2.23 millimeter. Okay, so because you see 2.23 millimeter is so minimal, so that it can resist diagonal force here. Okay, so moving on to the second problem. Say we have here two blocks of wood that are glued together. So we have here a discontinuity between this member, and of course, as mentioned on the shear, as noted in the principle of shear stress, that discontinuities are subject for shearing stress, like a glued section or a grains in wood or a built-up sections. So those are the considerations. So in here, it is obvious that the component of P will become your shear or the cutting force, or what we call the tangential force that will be transmitted on X. Okay, so what will be the shearing stress in the glue? So basically, we will just have to separate the free body diagram. So perhaps you can consider the right portion. Okay, so this is the right portion. Of course, we're going to consider the diagonal of the glued section here, and then have here the P, and as a reaction, an oppositely directed P here as a resistance of this glued section. Say this is also equivalent to P. So by definition, tangential force is a force tangent to the surface. So this is the surface, so we're going to have a tangential force here. Say I'm gonna label this as V. Okay, so remember that P here is your mother force and V is just a component of your mother force, and therefore all we have to do is to draw a perpendicular force on that V, so that will be the other component. Okay, so this is the other component. So V here is a component and that will be the other component. Okay, so normally V here is termed as P tangential. Okay, isn't it? And the other component usually is P normal. So when we say normal, it is perpendicular to the surface. And if we say tangential, it is touching the surface, okay? Or parallel to the surface. Okay. So next, we're going to solve, of course, the value of P tangential by considering the inclination here. See, this is 45 degrees. So consequently, the other angle or the complementary angle of 45 degrees is also 45 degrees. So we will be having no problem with the calculation whether we use sine or cosine. But for sake of discussion, in essence of discussion, we need to emphasize how to transfer angles here. So again and again, I've been introducing this. Say we have an angle referred to the horizontal. You'll just have to draw a perpendicular plus a vertical line, and this is also the angle here. So we're going to do that here. Remember that P normal here is actually the perpendicular line. Okay, so perpendicular and a vertical. So anyway, if we cannot relate to this on this particular section, we can have this one. If this is theta, that is also theta, meaning this is the slope plus horizontal, that is theta. Slope plus horizontal, that is theta. Slope plus horizontal, this is theta. Okay, so do not be confused on that. So in this case, this is the slope referred to the horizontal. Okay, so this is the slope plus horizontal. This will now be your angle 45 degrees. And it is evident that your tangential force is adjacent to the angle 45 degrees. So if that is the case, we can solve for the tangential component by using P times the function of cosine. So this is P cosine 45 degrees. And in the problem, we have a fixed value for P. We have 15 cosine times cosine 45 degrees. So this is actually the tangential force, which is equivalent to the shear force. Okay, so by that, we will now use this formula. Tau is equal to V over A. However, we need to get the value of X here, because we cannot really use this one as the area of shear. So this is the cross-sectional area. However, a diagonal cut will be having a longer length here comparing to the 60 millimeter here. So therefore, let us utilize this right triangle here. Okay, so this is right triangle. Say this is X, this is 45, and we need to get the value of X using the given. So what is given here is the 60 millimeter width. So observing the given, the available data here, we can now use sine function 45. So opposite is 60. Hypotenuse is X. Therefore, X is equal to 60 all over sine of 45 degrees. Hence, we can get the value of X to be equal to 84.85 millimeters. Okay, so we are now ready to use this. So our V is 15 cosine of 45. So this shall be multiplied to 1000 to make it in newtons. And then the area is actually X, the value of X multiplied by the thickness. And the thickness is found to be 30 millimeters. So this time we're going to substitute the value of X. Okay, perhaps we can reflect what we have computed, 84.85. Okay, so as simple as that, we can now directly derive the value of the shear stress in the glued section. And that yields to 4.17 megapascals. Okay. So moving on to the third problem. So this is quite similar problem to what we have discussed previously. We have here two plates that are connected with this 425 millimeter diameter bolt, and if the applied force is 125, we are going to determine the following: the shearing stress on each of the rivet, and then the bearing stress in each rivet, and also the maximum average tensile stress in the plate. So letter A, shearing stress in each of the rivet. So tau is equal to V all over A. So what we do is, of course, say I'm going to use this illustration for my free body diagram. What will be the force in each of the rivet? So if this is the setup, there's no condition telling what is the distribution of this 125 on each of the rivet. We will just assume that these are equally divided on each of the rivet. So if we're going to consider a cut section here, say there will be resisting shear forces on each of the rivet, and as we can see by summation forces horizontal, we can just say that 125 will just be carried equally by these 4 rivets. Okay, so 4V. So therefore, V is equal to 125 all over 4. And that will be equal to 31.25 kilonewtons. Okay, so no problem with the area because the area is just the cross-sectional area here. So we can see it on the cut. Okay, so the cutting section passes through the cross-sectional area of each of the rivet. So the shearing stress now would be readily derived. See, this is tau. We have here 31.25 times 1000 all over the area of the circular cross section of the rivet, that is pi over 4 times 25 squared. So in here we can have the value of tau, and we have 63.66 megapascals for that. Okay, so next, what about the bearing stress in each of the rivet? So the same principle. So the bearing stress will be P all over 4, or the bearing force is just equal to P all over 4. So just the same, we are going to substitute out of the formula, the bearing stress formula. Okay, so we have here 31.25 times 1000. So this time the bearing area is the contact between the rivet. So if we are going to illustrate that one, see, we have here the plate. See, it's the hole in it. Okay, so remember that talking about the bearing, we'll just have to utilize diameter. See, this is the diameter, okay, times your thickness. Okay, so diameter times thickness. So anyway, we know the diameter, and we also know the thickness. Diameter is 25 multiplied by the thickness. Okay, so the thickness here is 35 millimeters. So this is 25 by 35. So therefore we can derive the bearing stress on each of the rivet. Okay, so we have here 35.71 megapascal as for our bearing stress in the rivet. So for the third unknown, what is the maximum average tensile stress in the plate? Of course, we are going to consider the reduce area. Okay, why reduce? Because some of the area were occupied by the rivet. Okay, so if we have a tensile type of force, we should account the space that is taken by the hole. Okay, but if your force is compression, though we have a hole here, does not matter. So we're going to neglect that one. Okay, so I hope that is clear. So letter C, we just have to apply this. Tensile stress is equal to P all over A. Okay, so what will be our P here? So it is no longer 31.25 because this time the force is on the plate. It is not on the rivet. So our consideration is the force on the plate itself. And the force in the plate itself is 125 kilonewton. So we do not need to divide that, okay, because we are referring to the plate. So 125 times 10 cube all over the area. Okay. So the area, we have a width here equivalent to 100. Okay, so we can see it 100. And then 100 will be reduced. We're going to deduct here the 2 16 mm. Okay, where there are 2 16 mm that was taken from your original cross section, and then multiply it by the thickness, and the thickness is 35 millimeters. Okay, so now tensile maximum, so we can place here maximum tensile stress is equal to 52.52 megapascal. So this is the maximum tensile stress. Okay, so that's it for this problem. So moving on. So here we have the fourth problem. So in your engineering mechanics, we know that if we have a pin support, you see this is the pin support, there will be two reactions. Okay? There will be two reactions. Say a horizontal and a vertical reaction, say RH and RY. So the resultant shall prevail on these two reactions. Say this is the reaction, and this reaction will tend to pull this bar out of the reaction. So the tendency is double shear. So this is a double shear setup actually. So there will be two cuts here. Okay. So the first step here is to determine what is the pin reaction here. So as usual, we're going to draw the free body diagram. Say this is the bar, and the bar is actually resting on this wall. So there will be force against the wall. So remember, any surface has a force, a reaction force that is perpendicular to the surface. So if this is the surface, that is a vertical, and a perpendicular line to vertical is actually a horizontal force. So this is the reaction at the wall. Say this is reaction at B. And for the pin connection, there will be RAY and RAX. So basically, we'll just use the equilibrium equations to come up with RAX and RAY. Let us note here that this bar also has its weight, that is 1,500 kilograms, located at the centroid. Okay, so we'll just have to get the center of gravity. Actually, that is a mid dimension of this bar. So this is 1,500 times 9.81. We have 14,715 newtons. Okay. So next, RAY could be readily solved because we can see here that there are only two vertical forces. Okay, so therefore you can just say summation forces y is equal to 0. You can just say that RAY going upwards minus the weight 14,715 shall yield to 0. So in short, RAY is directly equal to the weight 14,715 newtons. Okay, what about RAX? So it's also clear that summation forces X, it's also clear that RB is simply equal to RAX. However, we do not know yet the value of either RB or RAX. So what we do is to take moments at A, okay, to solve for RB. Say this is summation moments at A is equal to 0. We have a clockwise rotation of the weight, say 14,715 times half of 8, it is actually 4, and then minus a counterclockwise RB with a moment arm of 7. So this shall now equate to 0. Hence, RB is equal to 8,408.57 newtons. Now, this is also equal to RAX. So, having both components, we can now get the mother force of that components. Say RA is equal to the square root of RAX squared plus RAY. This is also squared. And then RA is equal to square root of, what is RAX? 8,408.57. Okay, let us square that one. Then we add RAY, 14,715 Newton. That is also squared. So you can find here RA. So we have 16,948.02 Newton. Okay, so this 16,948 will be actually the cause of your shear. Okay, so if we are going to have a side view here, say this is your reaction RA, so this will cause a double shear, okay, parallel to the force. Okay, hence RA is divided by 2 to get the shear force because we have a double shear. Therefore, V all over 2A. Okay, so we are familiar with this formula. We'll just have to double your area if we have a double shear effect. So in this case, we have 2 cuts for the rivet. So hence we have V here is half, 16948.02. So this is actually divided by 2, and the area is the area of the diameter. Okay, so actually we are getting the diameter, so pi over 4. Diameter is unknown. So this is diameter squared. Perhaps we can place here the value of the allowable tau. In your problem, it is 80 megapascals. So you just have to place it here, 80, and then by cross multiplication and by manipulation, taking the square root, we have 11.61 millimeter. Okay, so perhaps you can round that to an exact value for the diameter, say 12 millimeters. So we're going to use 12 millimeter diameter for the pin connection, whether your pin connection is a bolt or a rivet, or it could be a nail. So it really depends. So next, so problem number 5. If bar BC weighs 100 kilogram and cable AC is 75 and it is limited to tensile stress of 70 megapascal, what is the heaviest RC pipe that will be placed in the system shown? So you have already done this, okay, from the cylinder. From the cylinder, we're going to have your X and Y axis, okay, and then just place your loadings. Say this has a weight, it is actually unknown, and then of course the reaction, okay, the reaction of the bar towards the cylinder, and then this reaction will be transferred to the bar because they are actually pushing each other. Say this is the bar, and then from that we have here RBY and a value for RBX. So let us take note of the distances here. We have here 3 meter and a 6 meter here, plus a cable tension, okay, at C. See, this is tension C. So how can we connect now TC and W? Of course, we will work first for this variable here. Say, I'll just designate that as Q. So Q here will be transferred on the bar. So relating to W, W is a vertical force, so therefore we'll be needing the vertical component of Q. Say this is Q vertical, and we also have horizontal component of Q, QH. Okay, so to be able to express this in terms of Q, let us have a reference angle. Okay, so basic, this is just 38 degrees. Therefore, this is perpendicular plus a vertical. This is also 38 degrees. So theta is also 38 degrees. And FBD of the cylinder, we can just say its summation forces vertical is equal to 0, okay, negative W, that is going downwards, plus an upwards component of Q, which is QV. This shall equate to 0 to attain equilibrium. Then we'll just have to express this in terms of Q. So this is Q cosine of theta, since we have an adjacent force to the reference angle. Perhaps we can express this in terms of cosine. 38 degrees. And therefore, W is Q cosine of 38 degrees. And it is obvious that to relate TC and the Q, we just have to take moments at B. Okay, so this is point B. So FBD, or the free body diagram of your bar BC, we have summation moments of B. So is equal to 0. We have Q times 3. Okay. Meron bang weight yung bar? Yung bar BC daw may weight. Of course, we really need to consider also the weight. So this is the centroid. We have here a weight. Okay. So weight here will be equal to 100 kilograms times 9.81, and that equates to 98.1 newtons. Okay. And what is the distance of W? Of course, we will be needing here the triangle, okay, of the inclined bar. What is the dimension of the bar itself? It is actually 9 meters. So that if this is 38 degrees, we will be needing this dimension. Okay. Say, let us delegate that as Z. So by function of what function? Cosine, we have Z all over 9. So here we can determine the value of Z. So we will be having 7.09 meters for the value of Z. So why do we need Z? Because it is the moment arm of W. Half of Z is the moment arm of W. So Q times 3 plus another clockwise rotation, say W times Z all over 2, okay, minus TC times the moment arm of TC. Oh, we do not know yet the moment arm of TC from here up to point B, so we'll be needing this distance, okay. So this distance. So let us use this again. See, I'm going to label that as Y. Actually, we can have a Pythagorean relations on the 3. Say 9 squared is equal to Z squared plus Y squared. Okay. Hence, 9 times 9 is 81. Z is 7.09 squared. And then we can get the value of Y. Okay. So the value of Y is 5.54 meters. Okay, so next, okay, so we can place it here, 5.54 meters, and this equates to 0. So we will just substitute all the data here. What is the value of Q in terms of W? Because by the way, perhaps we can have some variations on our variables here. See, W, this is BC. And W is actually the weight of the cylinder here, which is the unknown. So we can directly substitute Q in terms of W so that we will yield to the answer directly. Okay, so we can simplify this. Q is equal to W over cosine 30 degrees. Okay, so Q is W all over cosine of 38 degrees. Okay, this is multiplied by 3, and then plus the weight of the bar BC. Weight of bar BC is this one, 98.1 newtons. Okay, so here it is 98.1, and then say is 7.09 all over 2 minus TC. So TC, we can derive this out of the given stress limit equal to 70 megapascal. Say, take note that the cable is 75 millimeter in diameter, having an allowable of 70 megapascal. So basically, sigma is equal to P over A. Okay. So sigma is 70. Okay. And then P, here's the tensile at C. See it that this is the force at C, TC. And then the area is pi all over 4 times 75 squared. So you can get here the value of C equal to 309,250.53 newtons. Okay, where's that? Here. We just place the value here. Okay, 309 250.53 newtons times 5.54. So this is equal to 0. So of course you can now manipulate and get the value of W. So we have 449,927.63 newtons. Okay, so this is the largest weight considering the allowable stress on the cable. Okay, so this completes our solution for the 5 problems involved in your last quiz. So I hope that this helps, and thank you for listening, and see you on the next video.